Hello and welcome to part 2 of Dev Maths and Stats Refresher Course Lecture 8. Now we're going to look at variance, and this builds on the idea of expected value. So suppose we have a random variable, expected value x, you can write as mu. Then from that you can get the variance of x, and it's defined in terms of expected value in terms of this. So it's the difference between whatever you're going to get for that random variable minus the expected value. So it's like how far away is each value of x from the expected value squared. So it's that expected difference from the mean squared. And it's often written like this, sigma squared, small Greek s squared. So the definition is the variance of x is this expected value. This can be simplified to get this, which is often easier to calculate. So it turns out starting with this definition, you can show quite quickly that the variance of x is equal to the expected value of the random variable squared, and then just take away the expected value squared, mu squared. And I'll show you how to do that to justify it, but the nice thing is that having gone through all that quite complicated proof above about why expected value of a plus b is equal to expected value of a plus expected value of b, now you can use it to quickly show this, that the variance of a is equal to this kind of awkward expression. So it's expected value of, see, this makes sense, but you might think to yourself, before I tell you, what would you expect this to be? The expected value of x minus mu. Okay, you should be able to tell me that the expected value of this would be 0. Two ways of looking at that, because obviously you expect x to be equal to mu. So the expected value of the difference between these things should be 0. Also, if you saw this as two things, a and b, you could split it up to say it's the expected value of this minus this, which would give you 0. So that's why you don't use that in that form, because it would just be 0. So to get an idea of how far we expect to be from the means, give us an idea of the spread we're going to get in these values, we do this and we square it. Now what we can do with this is the part inside, before we calculate the expected value, you can just multiply this out. So it's the expected value of x squared minus 2 times the mean times x minus mu squared. And let's give it the full proof. You can split this up because this is just using the rule that this plus this plus this, you can just add the expected values up. Actually, no, I'll skip one line. This I could say it's plus expected value of all of this stuff here. Okay, I will do it to mu x. Gosh, look at that mistake there. That should be plus because mu squared is plus. Plus expected value of mu squared. Now I really like this row here because we've just used the expected value of a plus b to split these things up into a plus b plus c to generalize it. Now we can use the other thing, which is about constants times, once we've done this one, because you can't do much with this. That just stays there. You have to calculate that. But this bit here, we had that rule about the expected value of kx is equal to k times the expected value of x. And this all here is just a constant, because mu is whatever number you get for the expected value of x. This is just a number. So that whole minus 2 mu you can take outside. And this one here comes from the other bit, which is the expected value of a constant is just the constant. So mu squared is just a constant number, so we expect it to be equal to whatever it is. And finally, the last bit of the magic, if you call it magic, a kind of magic. All sorts of things. It's a good job this eraser is very good. X there. The expected value of x is mu. So that's what mu is. So finally you've got it. Because here we've got minus mu squared plus mu squared, so it's minus mu squared. So the variance of x is just equal to the expected value of x squared minus mu squared. And that's using the expected value simplifications we had before. So you can apply this because in a particular case, if it's a discrete value variable, random variable with a list of values, you'd calculate it like this because this is the expected value of I minus mu. So that's using the original definition. So you can take each value, work out the distance from the mean, multiply it by the probability of getting that value, or you can use this one, which is often simpler to work out. So it's just square all the values and multiply those by each probability, add that all up, and after you've done all the addition, then just subtract mu squared at the end. When it's continuous, it works out very similar, just that you're integrating instead of adding with a summation. Just to then make it more interesting, instead of having simple random variables like this, what happens if there's conditional variance where the probabilities are depending on something else happening? So you have conditional variance, so that in here you just replace the probabilities with the conditional probability based on something else. So to make it concrete again, in the situation above where we've got rain-fed agriculture, which would be higher, the variance of yields or the variance of yields given the information that rainfall that year was 0? So just think to yourself for a second, pause the video and think, which should be highest? Variance of y, yields, or variance of yields given that rainfall was 0? Okay, I reckon that probably this would be higher, because the assumption I'm making is that if rainfall was 0, that means in a rain-fed agriculture you would get practically 0 crop, almost be entirely failure. So every time you get rainfall 0, close to 0 yield, so very little variation. Whereas in general yields, if you don't know that information, this is covering all the situations from too little rain to too much, everything between. So this would be much bigger. Okay, so that's starting to get into when other variables come in, but expected value and variance really just relates to a single random variable. Now, what we want to start doing is looking at how two or more random variables influence each other. So the first thing to think about there is covariance. So here we find that covariance of two random variables is defined like this, and so this is saying how far is x above what you'd expect x to be normally, and how far is y above what you'd expect it to be normally. So the covariance is the expected value of this. So it's that huge long thing like this, and then I'll leave it as exercise for you, but if you multiply this out and use the simplification rules that I showed you above, you can show that it comes out like this. So it comes out to be the expected value of x times y, which is this first part here, subtract mu x times mu y, doing pretty much the same procedure we just did above. So there's two ways of calculating it. Calculate this way, which is based off the basic definition, or calculate it using this way, which is often simpler, which is based on expanding this and using the rules for expected value. And then this is for when it's continuous. So this is what you can show by expanding this out and using the expected values. So that's covariance. The final thing you can get from covariance is the idea of correlation. And this is written as rho, which is hard to draw by hand to make it always looks like a P, but I think it's a Greek R. And so the correlation coefficients of x and y is equal to the covariance, but after you've got the covariance, then you divide by the standard deviation of x, standard deviation of y, which is the variance as defined up here, square rooted. So you square it, which has an effect of what's called normalising it, because as we'll see, when you calculate covariance, and we'll look at examples of this in a minute, covariance can get very huge, can get very low. Whereas when you divide by the numbers like this, it means that the correlation coefficient gets trapped in that range that you're all familiar with between -1 and +1. So it standardizes it, so you can compare different situations. So that's correlation coefficient. Okay, so in the next video, we'll look at some examples with particular values. But for now, thanks for watching.